with not further talk to you, and the floor is yours, Andrea. Yeah, thank you everyone for joining.
Okay, thank you very much, Julian, for the nice introduction, and thank you very much for inviting me for this talk. I'm very looking forward to present, I don't know, my view, what I know, what I've been learning during my research, during my PhD on Intumescent coatings. So I'll start sharing the screen so you can all see my presentation. And I'm gonna press pointer, okay. Can you see my presentation?
Yes.
Okay, fantastic. So, first of all, today I wanted to discuss about the main topic of my PhD and the research I've been focusing over the last few years. And I entitled the presentation of today, Intumescent Coating for Fire-Safe Structures, How Do They Work and How Do They Really Work? And what I'm gonna try to do today is try to answer these questions, or at least to give you additional information about this topic and what I learned about it and what might be helpful for you and your interest in your profession. So first of all, steel. So steel and steel structures are increasingly popular as a main structural material in construction because they have several advantages. So the first one is the outstanding strength and ductility of steel, their durability, particularly related to the new paints and the new environmental treatments that steel can get and achieve a very good environmental durability. Then architectural reasons and constructability, because steel and steel structure allows prefabrication and modular construction. So today we are able to build tall, thin, and beautiful looking structures like the one shown in the slide. So for example, the National Museum in Beijing in China, or the Shard in London. But what I've been looking into is that how the future is bringing us and what are the new designs of the future. For example, the Dubai Towers in Dubai and the Cobra Tower in Kuwait. So these are some preliminary designs of potential structure for the future. And what I see, apart from this, the beauty and the very exciting structure, I'm thinking about what are the challenges related to this scenario and what could be the new challenges of the future and the future of tall steel structures. And for sure, one of the challenges, it would be fire. And this is an example from 2005, the Windsor Tower in Madrid. And because when a steel structure is exposed to fire and high temperature, they usually experience a strength and stiffness loss. And if, for example, you go and you check on the Eurocode 3, when you check like 600 degrees, which is not a so high temperature for a fire, we usually expect, I don't know, 1,000, 1,100 degrees, you can expect about 50% decrease in effective yield strength compared to ambient temperature. So it's definitely a big a reduction in the mechanical properties at not such a high temperature. In addition, steel structures can experience thermal deformations that usually thermal deformation due to, can you hear me? Okay, thermal deformation due to fire. And the fire, the deformation can be large and they can create some sort of instability and structural instability and possibly they can trigger progressive failure of the structure. So the normal and the common traditional way to solve this solution is to use thermal barriers of different natures. And they're usually characterized by low thermal conductivity or high specific heat. And their aim is to limit the thermal penetration into the load-bearing structural elements. So therefore limit the temperature rise of the structural elements and the structural substrate. Some examples are, for example, some traditional examples are concrete encasement. So you mainly wrap the steel element, in this case, the steel column with concrete, and concrete is sort of acts as an insulation material around the steel column. Or you can use some flexible blankets around and wrap the structure with flexible blankets. Use traditionally board system, usually based on a gypsum plasterboard, or a solution that usually not very aesthetically pleasant, but is a solution that you usually see in car parks, is you can apply some cementitious-based spray-on systems. And what you can see here, you can see a new solution that is so-called, is represented by Intumescent coatings, known also reactive coatings. This is a solution that it looks like, as you can see here in the slides, it's like as a paint looking at ambient temperature, but when it's exposed to heat or sufficient heat, it swells and it creates a thermal barrier that protects the steel substrate from the fire. So this is, so you can see an example before the fire. So this is an I-beam coated with Intumescent coating. And then if after the fire, you can see how the beam, how this beam section would look like. So char that is characterized by low thermal conductivity and the low density that insulates the structure from the fire and keeps the temperature down of the steel substrate. And this is an example of a calorimeter test. So it's a paint exposed to heat, and you can see how the coating swells. And the Intumescent coatings usually called like that, and they're specific because they are characterized by the Intumescent process. So here on the left, you can see before heating. So if you can imagine like a steel plate coated with Intumescent coating. So this is the virgin coating. Then when it's exposed to heat, the coating starts melting, and the melting starts releasing gases. And the gases are trapped into the molten coating, you can see here. And this is called like reaction stage. Then the char starts charring at the surface, and then the char progresses towards the back of the coating. And finally, we have char changes. In particular, in oxygen-rich environment, you can have oxidation of the char. And this you can clearly see, for example, in the color change. It changes from a a black, dark char into a white one, which is oxidized at the surface. This process usually occurs into 4 different zones. So they're usually characterized by different temperature ranges based on the different fire exposure, but also the different products. And the first one is the so-called melting zone. Then there is the reaction zone, charring zone, and char degradation zone. As you can see, there is a big scatter in the temperatures because in the literature you can find a big amount of different products and different fire exposure and heating conditions. So what Intumescent coating brought to the market is several innovations and several advantages compared to traditional solutions. Because you can see here, for example, in London, some station, you can see that with Intumescent coating, you can have a thin, Intumescent coatings are thin and lightweight. They can produce attractive visible structures. They can cover complex details, like for example, steel connections, but also you can see here this very complete structure you just coated with a coating in a very nice way. Then the coating can be applied on-site or off-site. And finally, they can keep the same geometry. And this is a very important aspect, for example, in the case of in a rehabilitation of heritage building or historical sites where you need to achieve this higher, due to renovation, you need to achieve a higher fire performance, but with the same geometry without changing much the structure. So this would be a very interesting solution. But also, of course, there are some possible drawbacks compared to traditional solutions because the cost of Intumescent coatings are always a big question because depending on the size of the job, you can have cheap, they can be relatively inexpensive or like this comparable cost compared to traditional solutions, or they can be very costly due to the main work that you need to apply the coating. And also at the same time, another question is the maintenance during the service of the structure. Is reactive coating, so therefore you need to ensure that the coating is active and is able to react during the design life of the structure. So today this Intumescent coating have a great success and we can build these sort of structures. You can see a very light steel structure and with a high performance in case of fire, and Intumescent coating became a mainstream worldwide fire safety solution for steel structures, but also beyond, because the industry and also the research community you can see that this coating, I mean, different individuals and professionals are looking into applying intumescent coatings also in concrete, for concrete structures, in order to avoid, for example, fire-induced concrete spalling, but also to increase the performance in fire of timber structure or engineered timber products. Regarding the current design framework, as many other structural materials and fire safety solutions, the performance of intumescent coatings is commonly assessed adopting simplified engineering methods that are based on a unique fire scenario that is usually represented by the standard temperature time curve in fire resistance furnace test that you can see here on the left. This curve is characterized by high heating rates at the beginning of the curve and high gas temperatures. And this is conceived as the typical concept of having a high temperature would represent a worst case scenario for your structural condition or your structural element. So high temperature. And in the case of having a steel structure or a steel element, when is unprotected and exposed to standard fire curve, you can see something like that. So the steel starts increasing temperature due to thermal inertia as a bit of delay compared to the gas temperature, and then start following after reaching a certain temperature, start following the fire curve. Instead, if you have a protected steel element, that it could be really intumescent coating, but also any material, what you can see that the temperature rise in the structural element is actually delayed, and of course with different amounts in different depending on the different material. So as I mentioned, there are some different engineering methods, implicit engineering methods to design intumescent coatings, and the first one is the tabulated fire ratings according to the standard EN 13381 part 8. And you can see, for example, that usually intumescent coating manufacturers, and out of some fire resistance tests, they would produce tables like that, where you can specify which element you would like to protect. For example, in this case, of beam and columns with open sections. Then you see the fire resistance class. In this case, you want to achieve a 60 minutes, 1 hour fire resistance. Then the structural engineer, usually based on the utilization factor of your structural element, can decide the design temperature, or you can also take with a sort of a priori approach. And then you define the section factor, which is the ratio between the exposed area of your steel section mainly divided by the volume of the steel. And by crossing this information, you can get the minimum required dry field thickness of your coating. Dry field thickness means when the coating is dry, not when it's wet, in order to achieve this specific resistance class. Another method, still in the same standard, but in the Annex E, is to sort of follow a performance-based design approach where you can calculate the effective thermal conductivity of your coating considering a certain fire resistant test. So what you can get is that you can get some certain curves for if you can plot the effective thermal conductivity, that is mainly the quantification of the thermal, of the insulating properties of your coating when it's exposed to fire with different temperature of the steel. And you can do something like that in order to understand the performance of the intumescent coating. However, the research and people in the field know that intumescent coatings are chemical reactive material, and numerous researchers have emphasized the influence of several factors on their effectiveness. So apart from the chemical composition, what we can expect is that the performance of intumescent coatings exposed to fire is influenced by several factors. And the first one would be, for example, the heating conditions. So for example, the fire scenario, the fire curve, or the heat flux it would apply on the coating, the substrate thermal conditions. So for example, the steel section factor that I just mentioned earlier, the initial coating thickness, and I mentioned earlier, the dry field thickness, and the fire tester methodology. For example, the oxygen content in your testing apparatus. And this is an example for, that I showed you earlier. This is the same I-beam. This is from my master thesis at the Technical University of Denmark. And what you can see here, you have like an I-beam that is protected with intumescent coating. And when it's exposed to a fast-growing fire, like for example, the standard fire-resistant curve, you can see that the coating swells and it creates a very thick and dense char that protects the steel beam from the fire. Instead, what I did, I also exposed the same coating under a different time curve of fire. So the fire in this case was reaching the same high temperatures, but with a different heating rate. So it was getting in a slower way. So you can see here that the coating in this case, it mainly didn't activate properly, and it created this very thin char that actually didn't protect the steel beam properly. And this is a problem. This is very important. And this is another example that I showed you earlier, like for example, using a testing apparatus that is called cone calorimeter, that you can see here, I have a steel plate coated with intumescent coating, and you can see that at the end of applying different conditions, you can see that I got different swelled coating and at the end of the thermal exposure. And this is very important for your structural implications, because you can imagine if you have a coating that swells a lot and it creates a thick char, you can see that the temperature in this beam that is exposed to fire is not going to increase much, so you're going to have small displacements in case of fire. In the case that the coating swells a bit less and it insulates the steel beam a bit less, you can see that here the beam at this point will deflect more. And this is the case when you have the coating that is swelled much and you have like a poor insulating performance, and the steel beam will deflect much more. And this is very important when you do structural assessment of, structural assessment of your structural system when it's exposed to fire. And what I see as a problem is that the current procedure don't represent a comprehensive design practice to ensure the fire safety of structures. So they don't assess the physical and thermal behavior as well in intumescent coatings. They only look into the temperature of the substrate. They're based on a single heating condition. So they don't address, for example, a range of potential heating conditions that might occur in a fire. And also from the literature, you can see that there is no clear understanding whether the standard fire resistance test results can or cannot be extended to other conditions, because sometimes they are excessively on the conservative side and sometimes they are severely on the unsafe side. And in a world moving towards performance-based design solution, there is a need to fundamentally comprehend how different factors might influence the effectiveness of intumescent coating in order to formulate and validate numerical models of various complexity to produce realistic and reliable predictions, but also to build the principles of performance-based heterogeneous solution for robust design of fire safe structure that consider the effectiveness of intumescent coatings under a range of potential conditions. But also this would allow the higher level of safety and a well-defined level of safety based on in a way that we can allow a reliable performance and reducing uncertainty and risk. And this again would be able to optimize the design process and start comprehending where costs can be reduced, for example, when it's necessary to protect a beam or to protect a structural element, and when, for example, secondary beam can be left unprotected. So in my PhD research carried out at the University of Queensland within the UQ Fire Research Group and supervised by Dr. Malouk, Professor Jose Torero, and Dr. Juan Hidalgo, that you can see here on the right, I've been focusing on different aspects of intumescent coating in order to try to understand what are the drivers of the effectiveness of intumescent coatings, in order to see how structures, fire safe structure can be designed in a reliable way. So the thesis and the PhD produce a lot of informations and a lot of very interesting results. And you can see here the journal publications, and also there are several conference contributions that I written with my authors and co-authors during my PhD. And this is mainly all the information I'm presenting today you can mainly find in these scientific papers in the literature. But if you have any question, and of course you can find everything in my PhD thesis, but if you have any question, I'm more than welcome to explain to you any of these aspects. So in terms of the PhD research and objectives, what I ask myself is that what is the true effectiveness of intumescent coatings? And particularly related to the presentation of today, do these intumescent coatings work? How do they work? And how can we ensure if they work? So the main objectives of my PhD were the development of an experimental methodology to accurately study the behavior of intumescent coatings. This one also to characterize the thermal and physical response of intumescent coatings, and also try to get an experimental understanding on how different factors affect the effectiveness of intumescent coatings. For example, how the heating condition affects the behavior of intumescent coatings, how the initial coating thickness, what about the substrate thermal conditions. And the idea of my PhD is to select a commercial product from the market, have a detailed experimental characterization and assessment of the effectiveness of intumescent coating, and also to put all this information to contribute to the basis of performance-based design of fire-safe structure protected with intumescent coatings. So what is important to underline is that usually intumescent coatings are categorized based on their composition and application, particularly in two different categories. The first one is thin intumescent coatings that usually are solvent or water-based, and they're usually prescribed in the built environment for cellulosic fire conditions, so for the standard fire resistance curve. They're usually applied of DFT, that is in terms of a few millimeters, and their swelling can lead to a swell char that is can go up to 100 times the initial DFT. So if we apply 1 millimeter of DFT, we can get up to 10 centimeters of swelled intumescent coating. On the other hand, there are thick intumescent coatings, or also called two-component systems, are usually epoxy-based, and in this case they are prescribed usually and applied in the hydrocarbon fire conditions, for example in the petrochemical industry. In this case, the DFT is usually in terms of a few centimeters, and they swell less in terms of up to 15-20 times the initial DFT. For this specific research, I selected a solvent-based thin intumescent coating that is a mainstream worldwide commercial product that is available in the market everywhere in the world. It's usually applied for structural steel in the built environment, and you can achieve, depending on the initial DFT and the size of the structural element, you can achieve up to 120 millimeters fire resistance. And it's a fast track and self-priming coating, so no primer or top coat was required. So how to start the research? The first step for my research was to carry out TGA, which is, TGA stands for Thermal Gravimetric Analysis. And this investigates, so mainly takes a little bit of the coating in terms of a few milligrams, like 10 milligrams, and you put it in a furnace. And in the furnace, there is a scale, a very accurate scale, and you can track mainly, you can see here the curve from zero to 1. These are the curves from, you can imagine, from 0 to 100%, and how the mass of the coating would decrease at different temperatures. And this is the case of N2, so in a nitrogen environment, so no oxygen, and this is the case of air. So we had an oxidizing environment, sorry. You can see here the curves and how the coating decreases with different heating rates, and here in air with different heating rates. And if you do the derivative of this curve, you can see mainly how the reaction happens at different temperatures. And this is the difference between nitrogen and this is oxygen. What you can conclude from these experiments, so first of all, you can characterize the chemical reactions and thermal decomposition processes due to using this experimental methodology. And the main outcomes that you can get from these experiments is that the main reaction and thermal decomposition processes happen in the temperature between 200 and 400 degrees. So you can see here that the main reactions happen between 200 and 400 degrees, where you can see that mainly the first peak is the release of gases and the melting of the coating, and the second one is the Intumescent coating swelling reaction that usually happens between 300 and 400 degrees. And here you see in oxygen, you have a similar behavior, but the main difference you can see here, you have also some peaks above 550 degrees, and this is typically char oxidation and the oxygen that oxidizes the char, and this is an exothermic reaction, typically an exothermic reaction. So then the next point was to understand and try to define an experimental methodology in order to study how intumescent coating behave when you're exposed to fire. This was done by selecting a fire testing methodology called HTRIS, Heat Transfer Rate Inducing System. This system the concept of this system is to place a radiant panel that achieves a very stable temperature and move the radiant panel on a linear motion system, in a computer controlled linear motion system, and by controlling the relative position of the radiant panel and the sample, you can control the heating conditions. And this is a novel experimental test in fire safety engineering, and does have several advantages, because the first one is you can have a direct control on the thermal boundary conditions on the exposed surface of test samples. For example, by controlling the incident heat flux at the surface of the sample. Then has the ability to impose a wide range of heating regimes by simply moving the radiant panel back and forth, or faster or slower towards the sample. Has high repeatability between experiments, has low economical and temporal costs, for example, compared to standard fire resistant furnace, and also, which is very important for the case of intumescent coatings, because as well, they allow the visual inspection of the sample during testing, something that is very challenging during standard furnace testing. So this is, for example, how the system that I developed at the University of Queensland look like. So the first one and the previous one that I showed to you, it was the version 1, and then this is the version 2 that has, instead of the radiant panel I showed you earlier, this is 4 radiant panels, and they have like a total radiant area of 300 by, actually this is wrong, 400 millimeter square millimeter, and you can see that the radiant panel can move back and forth on this linear motion system using a stepper motor, and this also based on a rotating table. So then using you can see here a heat flux gauge, water-cooled heat flux gauge, is possible to do a calibration of the system in terms of, you can see that you can correlate the distance from the radiant panel surface with the incident heat flux at different distances. You can see here for this specific system that I use in my research, you can get up to 140 kilowatt per square meter by simply controlling the distance between the radiant panel surface and the test sample. And in this way, by using your computer-controlled step motor and linear motion system, it's possible to control the radiant panel and reproduce mainly any sort of fire scenario. Like, for example, have a constant incident flux, have a linear increasing incident heat flux, a quadratic heat flux, but really any curve that could be reproduced using this methodology. Regarding the experimental investigation and what I tested during my PhD, first of all, based on the size of the radiant panel, I used steel plates that are mild carbon steel plates, 200 by 200 square millimeter, 10 millimeter thick, with a section factor of 100 millimeter to the power -1. And this, you can see here, the test samples. And the samples were professionally coated with an airless spray application using the intumescent coating I mentioned earlier. And in my experimental study, what I did is mainly to focus on 3 different aspects. The heating conditions, so I applied constant incident flux within the range 10 and 90 kilowatt per square meter, an linear increasing incident flux, different initial coating thicknesses, mainly 1, 2, and 3 millimeters, and also different substrate conditions. having the plate that is insulating at the back, using the steel plate with a heat sink at the back, or also a timber substrate. So if I apply the Intumescent coating on timber. And here you can see clearly the experimental setup. In terms of the instrumentation, the experimental methodology and the experimental setup was designed to analyze the effectiveness of Intumescent coating through a detailed characterization of the thermal and physical response during thermal exposure. In particular, I was trying to get as many information as possible to try to characterize the performance of the Intumescent coating when it's exposed to fire. So the first one, I used a high-resolution video camera that was placed on the side of my test samples that mainly I could track by doing some image analysis or video analysis that I can quantify the real-time thickness of the swelling coating. Then I also apply a series of thermocouples placed at the substrate that I can quantify the evolution of the temperature of the protected substrate, so the temperature of the steel plate, and also in-depth thermocouples that I could quantify. You can see here the transient temperature profile within the swelling coating while it was swelling. So what are the temperatures inside the coating while it's swelling? And finally, I also used, you can see here, IR camera, infrared camera, and this was used to quantify the temperature at the exposed surface of the swelling coating. Here, what I want to show you is a typical experiment that you can see here at the top. You see like the recording of the video of a normal camera. On the bottom left, you can see the video camera. On the bottom center, you can see the temperature in the steel and inside the coating. And on the right, you can see the swelling of the coating during the experiment. This is the case of 50 kilowatt per square meter. The test was 1 hour. You can see here the time. And, oh, sorry, I stopped it. And what you can mainly see, you can see the swelling of the Intumescent coatings. And what is interesting, maybe you're wondering why the radiant panel, and I'm going to play it again, you're wondering why the radiant panel, while swelling, is moving backwards. So what I was trying to do is I was trying to apply a constant incident heat flux at the exposed surface. And therefore, if the coating swelled during the test, the surface was getting closer to the radiant panel. So the incident heat flux would increase. So what I was doing, by quantifying the thickness of the coating, I was moving the panel back in order to keep always the distance between the surface of the coating and the radiant panel the same, to have always the same incident heat flux at the surface. And you can imagine that I got like a lot of information from these experiments that I started analyzing in order to focus on different aspects. The first aspect is the onset of swelling. So what I mentioned you earlier is that the Intumescent coating usually, and the Intumescent process usually happens with different zones or different processes. The melting zone, the reaction zone, charring zone, and char degradation zone. What is important and what is key for Intumescent coating is the swelling, in particular the onset of swelling. So I asked myself, what are the conditions that promote the onset of swelling? And particularly the onset of swelling, it would be defined as the end of the melting zone at the beginning of the reaction zone. And you can see here from the literature and the schema made from the literature review, you can see that it happens in a range of temperatures based on the different products, different testing apparatus and everything. But what is very important, the onset of swelling, because as I showed you earlier, there are some potential problems, like for example, incomplete swelling or coating melting that will not allow the coating to swell. So what I wanted to understand is to investigate which condition promotes the onset of swelling for Intumescent coatings and how heating conditions, in this case I use constant incident flux between 10 and 90 kilowatt per square meter and initial coating thickness 1, 2, and 3 millimeters, how this aspect would influence in the study. And what I did, the substrate thermal conditions were always the same. So I used a steel plate, 10 millimeter thick, insulated at the back. So the first result I did, you can see here, this is the result, for example, for 35 kilowatt per square meter. You can see here on the left axis the temperature. So this is the temperature that would follow uncoated steel plate exposed to 35 kilowatt per square meter, and this is the temperature that we follow a coated steel plate. Well, you can see that at a certain point there is a sort of bifurcation between these curves because mainly the coating starts the swelling process. So I defined the onset of swelling according to 2 criteria. The first criteria was, as I was showing now, the temperature evolution of the protective substrate. So the moment that this curve starts diverging from the uncoated steel, I define here as onset of swelling. And also I quantify the onset of swelling as a minimum swelling. And in this case, it would be 5 millimeters. So you can see that I define a certain range of onset of swelling for all the different experiments. And if I put together all the different experiments, you can see that I get a different time to onset of swelling for all the different experiments at different constant incident flux applied. And you can see that the coating would take a lower time for high flux because higher temperature and faster heating rate. But then at a certain point, up to below 20 kilowatt per square meter, I didn't register any onset of swelling. So I defined that the coating required a constant incident flux higher than 23 kilowatt per square meter for onset of swelling. And by this information, I could go back into my information, and what I could quantify the steel temperature and the mean coating temperature as the average between the steel temperature and the temperature at the surface at different heat fluxes. And what you can see that the temperature, the steel temperature at onset of swelling varied at different constant incident fluxes between mainly 250 and 100 degrees, having a higher temperature for lower heat fluxes, and also for mean coating temperature varied between 350 and 500 degrees. But you can see that the incident heat flux, the constant incident flux, or the history of heat flux has an influence on this, but also what I look at is also the influence of the initial coating thickness, because this is, for example, the difference between low, medium, and high dry field thickness applied on the coating. And you can see that if the coating was thicker, you needed a lower temperature at the steel while for onset of swelling. Then, in terms of the second study that I want to present today, is that focuses on what is the influence of the heating conditions and the thickness. So the objective of the study, I used the same experimental setup with the same radiant panels, the same steel plates, 200 by 200. But in this case, what I looked at is the influence on, the influence of the heating conditions. In this case, I used 6 different heat fluxes, 10, 25, 40, 50, 70, and 90 kilowatt per square meter. And the initial coating thickness, 1, 2, and 3 millimeter with the same substrate thermal conditions, so insulated steel plate. And I wanted to look at the influence of different parameters on the effectiveness of Intumescent coating. So these are some typical results. So you can see here on the left, low DFT, the results in terms of steel temperature and swell coating thickness, medium DFT, 2 millimeters, and high DFT, 3 millimeters, in terms of steel and coating temperatures. What is interesting about this, you can see that for the high DFT, that when you have a high thickness, the coating swelled throughout all the duration of the process, unless for the case of 10 kilowatt per square meter, that as I presented earlier, I was not expecting any swelling. And you can see here that in the case of 10 kilowatts, in the case, the gray curve, I didn't get any swelling. But in the case of the high DFT, the swelling continued during the whole process. And the temperature of the substrate, in all the cases, tended to between 300 and 350 Celsius degree. Instead, in the case of medium, you can see that the coating starts swelling and at a certain point stopped. And for example, and particularly, the coating didn't, in the case of high DFT, the coating swell up to 70 millimeter, which is a lot. Instead, in the medium DFT, you can see that the swelling stopped around something between 40 and 50 millimeter. Instead, in the case of low DFT, the coating stopped around 30-35 millimeters. So you can already see that the coating could swell more for higher DFT, but this is something that could be predicted because higher DFT means a higher amount of material, so means you have more material that can swell, really. But what's interesting as well is the fact that you can see for the case of low DFT, when you have swelling, I'll just show you that all the temperature tended to in a range of between 300 and 350. Instead, on the case of low DFT, when we have 1 millimeter DFT, you can see that in the case of red curve for 90 kilowatts, you can see that around 20 minutes, the coating stopped, the swelling stopped. And the temperature at that case, that was around 350, started increasing above this threshold. So as you can see, these are, for example, some charts that I obtained at the end of my experiments, completely different charts with completely different swelling. Of course, not much swelling for the case of 10 kilowatt per square meter and a very thick porous char in the case of 90 kilowatt. In terms of surface temperatures, you can see that the Intumescent coating behaved as an insulation material, as a thermally thick material, where you have that depending on the incident influx, the Intumescent coating goes into a sort of steady state condition on the surface, so a sort of like constant temperature at the surface based on applied incident heat flux. And in terms of conclusions, what you can see is that, first of all, the swelling process and the resulting swell thickness govern the thermal physical response of Intumescent coatings. Because, for example, if I start comparing the steel temperature with the swell coating thickness, you can see that the coating starts swelling, all the temperature tend to the same range between 300 and 350, but then at a certain point start increasing above 350 with the same thickness. In the case of high DFT, you can see that the coating keeps swelling during the whole duration of the test and never, only in a few cases, stop swelling and increase above 350 degrees. So mainly, during swelling, the substrate temperature tends to the temperature range 300-350. And this is, if you remember from the Tga experiments, I showed you that the Intumescent swelling reaction happens at temperature between 300 and 340. So when the coating is swelling, the temperature of the substrate, which is behind the coating swelling, is below the reaction temperature. That makes sense. And once the swelling is completed, the substrate temperature increases above this threshold. So this gives us a very important understanding on how the Intumescent coating swells. In particularly, if I remove the laser, you can see that the substrate temperature acts as an indicator of the swelling process, as the swelling reaction occurs in proximity to the substrate coating interface. So the coating, you can imagine here I have a heat flux that penetrates through the coating close to the surface starts swelling, and the gases released by this coating are mainly trapped in the coating. So the Intumescent coating swells and insulates the protected substrate by displacing the already swelled coating towards the direction of the heat source. And what you can see particularly, if I zoom in one of the experiments, you can see that the radiant panel gets closer and that the coating starts swelling. And as you can see, this part is already swelling, but then this part is sort of steady, but the swelling is pushing from here. So the coating swells very close to the substrate, where actually the reaction happens. And this is a very interesting and important aspect because it makes you understanding how the swelling of Intumescent coating occurs and what are the physics behind it. Particularly what is interesting is that then we start thinking, okay, how the Intumescent coatings, what happens if we sort of flip the reaction of the Intumescent coating? So you can see here, for example, a plate, the same steel plate, and here you can see a bit the cone calorimeter. So what I mainly did, I applied a heat flux. Instead of from the surface of the coating towards the steel, I applied a heat flux from the back of my plate and towards the Intumescent coating. So I mainly flipped the thermal gradient inside the Intumescent coatings. What you can see at the beginning, the steel plates start heating up. Then you can see here the creation of some bubbles because now the coating starts swelling. The coating close to the plate start releasing gases, but the coating next to that gases is not melted yet, so you cannot trap the gases for the swelling reaction. So the bubbles at the beginning are small, then they get bigger and bigger, until at a certain point you can see they create a sort of cavity that the coating delaminates until the coating completely is detached from the plate. And this makes you understand that it's very important how the swelling, the importance of the fire exposure, and particularly the thermal gradient within the coating when the coating is swelling. Then another conclusion is from the previous experimental campaign that I showed you earlier is that the measured in-depth profiles suggest that Intumescent porous charts has similar thermal and physical properties, regardless of the heating conditions and the initial coating thickness. In particular, if you can see here, we just mentioned that here is the depth of the coating and the temperature, and then the evolution at different times. So you can see that here, at depth 0 of the coating, so the steel substrate, you can see that we just mentioned that the coating has a very similar range when the swelling is not happening. When the swelling is happening. So mainly the coating starts swelling and the gradient is stretched between this thickness of the coating. But the difference is that in the case of a high DFT, the coating starts increasing temperature at the steel and the coating keeps swelling. So, and the temperature of the surface is a sort of constant based on the applied heat flux. So what happens is the thermal gradient is governed by the swelling coating, and mainly the gradient within the coating between the two temperatures, which is 300, 350, and the temperature at the substrate at the surface defined by the incident heat flux is stretched by the swelling of the Intumescent coating. And another important aspect is that the coating swelling process is affected differently by the heating condition than the initial coating thickness. Particularly the initial coating thickness that I show you here, applied initially DFT, governs the maximum swell coating thickness. So based on the initial DFT, you can get a maximum swell thickness. Then the coating stops swelling, okay? And here I mainly create an empirical correlation to correlate the initial applied DFT and the maximum swell thickness. And also on the other side, the incident heat flux at the coating surface governs the coating swelling rate. So for a high heat flux, higher temperature, high heating rate, I have a faster swelling coating. Finally, the last experimental campaign I would like to show you focuses on the substrate thermal conditions. So what I can show you here is that here I have my fire. In my case, I have a radiant panel that applies a certain heat flux on the surface of the coating swells, and I have my steel plate at the back. And what I've been doing so far, I've been isolating the steel plate. So all the heat that penetrates through the coating collects inside the plate, and no heat, in theory, or a small part, can leave the plate from the back because I used an insulating material. The question now is, what happens if I have a thicker plate? So I have a thicker thermal mass. And also I was wondering what happens if I apply my Intumescent coating on a steel substrate, on a timber substrate that has completely different thermal and physical properties. So in terms of this study, I wanted to investigate how the substrate thermal conditions affect the effectiveness of Intumescent coatings under the same heating conditions, and I just picked 50 kilowatt per square meter, and under the same initial coating thickness, 2 millimeter, okay, DFT. So what I used here, in order to replicate the different thermal boundary conditions at the back of the plate, I used different sample holders. So the first one is to reproduce a sort of adiabatic of insulated conditions. So you can see here my steel plate and the sample holder. At the back, I have 20 millimeters of mineral wool and then gypsum plasterboard. And this is a sort of reproduce my isolated conditions. Then I also developed a custom-made sample holder that I had my steel plate, and at the back there was another steel plate, and then there was a cavity where I could circulate water. You can see here water in and water out So there was a 10mm cavity for water circulation and then another steel plate at the back. And mainly by controlling the water flow inside my cavity, I could cool down my plate at different rates. And also I compared this case for the same coating applied on a CLT or timber timber sample. So what you can see again is that in terms of the surface temperature, since I applied 50 kilowatt per square meter, the temperature at the surface tended to a steady state conditions that lead to a temperature between 650 and 750 Celsius degrees. But what I registered by having different thermal boundary conditions at the back, I have different temperature at the steel substrate. So this is the case of the isolated steel plate. So all the heat get into the plate and I achieve a temperature about 350 degrees. And then I have 3 different cases where I mainly changed the water flow inside my sample holder to get a different temperature in the steel. Here in the heat sink case number 1, so a low flow rate of the water, is I got a temperature about 250. This is a higher flow rate, I got about 150. And this is the third case, I got about 100 degrees. And what is interesting is that in this case, in case of the swell coating thickness, you can see that the coating swelled in completely different ways based on the different thermal boundary conditions at the substrate or at an exposed surface of my steel plate. And as in terms of experimental outcomes, I showed that the substrate thermal conditions govern again the swelling of Intumescent coating, therefore the effectiveness. So this is the case, for example, comparison between the 3 heatsink cases with isolated cases and the timber case. And here you can see the different coating swelling at the end of the experiments. So this is with the high heat losses at the back, this is the insulated plate, and this is the timber case. You can see that in the case of timber, the swelling is much faster than in the case of the insulated steel plate. And this is because of the substrate thermal conditions that govern the swelling of Intumescent coatings because of their physical and thermal properties of the substrate. So in particular, what is the capacity of the system to concentrate and dissipate heat in proximity of the coating's substrate interface, where I showed you earlier, the reaction happens, and is the temperature that actually the reacting virgin coating is experiencing. So from the case of insulated steel plate, you can imagine that the heat penetrates through the coating and the heat starts collecting in the plate, and this is the temperature here start collecting and start increasing based on the thermal inertia of my steel plate. In the case that I have a heat sink cooled by water, you can see that heat penetrates, reaches the steel plate, but also is cooled at the back. On the other hand, if I have here, I have a coating that is exposed to heat and applied on a timber substrate, you can imagine that timber has different thermal properties than steel plate. And in particular, the thermal conductivity of timber is much lower than steel. So timber concentrates much faster heat at the surface, its surface, so the temperature of the swelling coating is faster. So as a consequence, I achieved high swelling rates, the highest swelling rates for timber substrate, so low losses at the back. And I achieved low swelling rate for steel plates with heat sink, so with high losses at the back. So in order to conclude, some concluding remarks that I would like for you to underline and bring home from today's presentation is that the first one is due to their advantages and innovations, Intumescent coatings represent an outstanding solution for ensuring the fire safety of load-bearing structural systems. Because what they do, they take the heat from the fire, they use this heat to feed their swelling reaction, and what they do also, they bring the fire mainly away from the structure that they have to protect. So a very efficient solution. But also I show you that there are several knowledge gaps in the understanding of the behavior intumescent coatings is supposed to fire. And consequently, there are several shortcomings and uncertainties in the design methodology of coated structures. And the presented research that I show you today, and my PhD in general, aimed at contributing to building the principles for the performance-based design of structural elements protected with intumescent coatings, and by explicitly understanding how different factors may influence their effectiveness. So first, I show you that by collecting a lot of information and having very well-defined thermal boundary conditions, I developed an experimental methodology to analyze the effectiveness of intumescent coatings through a detailed characterization of their physical and thermal response. And also, the effectiveness of intumescent coating is mainly governed by the coating swelling process and their ability to develop a thick swell porous char. And the swelling of intumescent coatings is a complicated process, but it occurs following specific physical changes and chemical reaction at specific temperature that I'll show you as soon as we change the concept or the thermal gradient within the coating, that mainly we have our virgin coating is at the surface, the coating stops swelling because mainly the concept is completely changed. And finally, this experimental research, I show how the effectiveness of intumescent coating is governed by the heating conditions. In particular, it governs the swelling rate. The initial coating thickness controls the maximum swelling of the coating, and the substrate thermal condition, again, controls the swelling rate. So if this is the whole system, that I have my incident flux at the surface, the heat that penetrates and reaches my coating that is swelling, and also I have some losses at the back due to the substrate. You can imagine that I have, if the same substrate thermal conditions, so isolated steel plate. For higher heat fluxes, you can imagine that, and I'll show you, you get higher swelling rates. But what happens if you change the losses at the back? So if you have higher losses at the back, you would get a lower swelling rate. Instead, if you have a lower losses at the back, you can imagine that you have a higher swelling rate. On the other side, if you have the same incident flux, the same heating conditions, and different substrate conditions, so a very insulating substrate like timber, or the heat sink with a very high flow of water, so a lot of losses, you can imagine that the swelling rate decreases because all the heat is mainly dissipated and doesn't reach the swelling of the coating, or the coating swelling. And if you increase the incident flux, you can imagine that you get higher swelling rate. Instead, if you decrease the incident flux, you can get a lower one. And the last point I would like to highlight is that there is the other research, that in this research, I used a solvent-based thin intumescent coatings that I used as an exemplar product. So this methodology provided an essential assessment procedure applicable to any coating, and obtained results are useful examples of the key information that can be extracted by this set of experiments. However, definitely we are working, but also invite everybody to push this research, that we need further research to understand if these outcomes can be extended to other products available in the market. And finally, as I mentioned today, I have been investigating my PhD, but of course, these are not all the questions related to intumescent coatings, because other aspects that are relevant for the effectiveness of intumescent coatings is, for example, what happens if you have a physical obstacle and you have hinder swelling, so the coating cannot swell? What happens? And then what is the long-term durability of and environmental degradation of intumescent coating during the life of the structure, particularly under different environmental conditions? And finally, as I show you, if we start applying the intumescent coatings on timber and concrete, what is the stickability of the coating with the substrate? Can we have any problem? And these are some open questions that I'll leave for discussion, but also leave for other researchers to hopefully answer in a short time. Finally, I would like to acknowledge my research team and my supervisor, my colleagues, my friends that have been helping me and supporting me during my PhD, and of course my current institution, Ghent University, that I'm working right now as a postdoctoral researcher. And finally, these are my contacts that feel free to contact me if you have any extra questions than the question that you can ask today, and I'll be very willing to help you and answer your questions. And now, if you have any questions, doubts that came out from the during the presentation, please feel free to ask them. Thank you very much.
Thank you, Andrea, for your amazing presentation. Really exhaustive and thorough explanation how intumescent coatings work and how different thermal boundaries and scenarios affect their behavior and the way they work. So we have some questions here in the chat. I'm gonna start reading the first of them to you.
Yeah.
And yeah, we'll see how the time is running, and we are gonna limit according to that. So from Roshi, he asks, a steel column inside a building or fire compartment is most likely to be exposed to direct flame impingement. How can the proposed radiant panel exposure be related to the real fire scenario?
First of all, very good question, very important, very challenging as well. So the main concept is, so what we did in the research, and particularly in this research, is to quantify and to try to understand fundamentals related to intumescent coatings, because what happens in the building industry, we do all this implicit engineering, we use all these engineering tools, but we don't have a fundamental understanding on how this coating would behave and what would change if you change the heating conditions, if you change the initial DFT, or if you change the size of, for example, your plate or your steel column. So what I wanted to do, we wanted to do in our research is that to use simple conditions that you can control easily to understand fundamentals. And I'm not saying that this will be a new design process to design intumescent coatings, because what you can imagine, I've been testing plates, and plates has a completely different behavior than, for example, an I-beam protected with intumescent coatings and with flame impingement and with different fine conditions. But what I wanted to show in this research is that some fundamental understanding that would help engineers and researchers to understand how this coating work, and also to bring a push to mainly improve the design methodology that we are currently using.
Thank you for your answer, Andrea. So on a more specific couple of questions regarding your study, Shivakuma posted two questions. The first of them being, what was the temperature of the substrate when the coating swelled, and what was the material of the coating?
So, so the coating, as I show you here, is solvent-based thin intumescent coating. So it's solvent-based, and this I don't have more information due to also proprietary agreements. And so is, I mean, intumescent coatings are usually based, so they are solvent-based or water-based, but usually they are based on a few components that allow the swelling of intumescent coating. So they are like usually work more or less in the same with the same process. And they can be that the composition, of course, can change with different fillers, for example. So this is all the information I can provide about my coating. And regarding the temperature of the swelling of the coating, I show you here in the Tga, you can have understanding on the material level. So this coating would swell in the case of a nitrogen atmosphere would swell between 300 and 400 degrees. Okay, and or the whole process would happen between 200 and 400 degrees. And but also show you when we go more on a heat transfer condition. So when I have my plate that is exposed to a incident flux and has a thermal gradient within its thickness, you can see that here I have a range of temperature based on the incident flux. So in the case of, if I look, for example, at the steel temperature, my swelling happened between 100 and 250 degrees. I hope I answered the question.
Sorry. So yeah, thank you for your answers. And following up with this Q&A session, there's a two-part question regarding the effect of or the behavior of the sample in a 2D or 3D environment. So the first part of the question says, it looks like the test specimen has a 2, if not 3D response, rather than swelling as a uniform thickness or the surface of the substrate. As regards swelling in the H3 experiments, as some well sagging due to gravity. So how was that phenomena accounted for?
Okay, thank you very much for the question. Very, very good one. So, first concept about the swelling. So, what the concept of the research is that the radiant panels has a certain size, and they were, as I mentioned, 300 by 400, and my sample were 200 by 200. And these sizes were decided in order to get an homogeneous distribution of incident efflux at the coating surface. But then what you can see, and also as you correctly highlighted, you can see that you have a constant, you have a sort of different swelling or some sort of edge effects at the coating edges. And how we solve this aspect, we just solve this because we start looking only at the central area of our coating. So we imagine that in the central area, particularly if I show you this case, where we look into the coating, coating surface temperature, we just look at the central area of the coating where we would expect homogeneous swelling, homogeneous thermal boundary conditions, and homogeneous surface temperature. So we didn't look at the edge effects, we just look at the center where we would expect like homogeneous conditions. And in terms of gravity, you can imagine that this coating, as I showed you earlier, maybe I can show you the Tga. So these coatings are applied in terms of millimeters. So the amount of mass is very limited. And what you can see also that at the end of the swelling process, about 40–50% of the mass of the coating is left. So what you can see is that the effect, the mass that the coating has is very low. So the gravity effect, they will be very limited.
Okay, thank you for your answer. And following up in that same sort of question, we have one regarding the behavior of the H and I beams you shown during your presentation. The attendee states these kind of beams are critical as regards of charring behavior around the flange tips. And he wonders how could the H3 experiments be used to study these in a 2D or 3-dimensional behavior?
So the concept of H3s is to have defined, very well defined and controllable thermal boundary condition in the coating at the material surface. So this is very useful for example, one-dimensional, like in this case, one-dimensional heat flux or heat transfer. In terms of when we look into 2D or 3D behaviors, then of course, one radiant panel would be not enough anymore. Because for example, if you're looking into columns, I can imagine that we will need for example, a 350 degrees exposure to recreate this one. But this is, I mean, what I wanted to highlight is that with this study and this methodology, I don't want to substitute the current version of the standard furnace, because I see and I'm aware that the standard furnace and like a furnace setup or 360 degrees setup compared to, and having a steel plate compared to I-beam or like a more complex shape would definitely have a better understanding on how a beam or a column would behave in a real fire and real building. So for me, it's like, it was for me is to understand the fundamentals and have a very physics and scientifically based approach to understand these aspects. But this, how to use H-trees for understanding I-beams and more complicated shapes, this is definitely needs further studies, and still for large-scale samples, the furnace is still the way to go, or at least we are not ready yet to substitute that.
Okay, thank you for your answer.
Just something that I wanted to underline is that the standard furnace is that something, I mean, you impose certain thermal boundary condition on the sample, but then what I'm trying to show you today is that how changing different aspects of your sample inside the furnace, for example, would you expect a different behavior in terms of effectiveness and in terms of protecting performance. But also what I'm trying to push and what I'm trying to also make people aware that one exposure for this kind of coatings is not enough, because if we design a coating in order to get a good behavior in the standard, in the case of a standard fire, it doesn't mean that the coating would behave in a good way or effective way in other conditions. And particularly when we do a performance-based design approach, how can we assure, since it's a reactive material, to have the same performance that we would expect in a very fast and growing fire, because the coating needs high temperatures as well. What happens if you have a slow growing fire? You cannot assume the same performance, and I'll give you evidence of that. So this is just the concept and the takeaway message that I would like to give to people.
Thank you. So following up with the conditions of your experiment, Stephen Mackrell thanks you for your presentation, and asks in regards to the testing with heating from the rear of the plate. Has any testing been conducted where the plate is coated and heated from both sides, and how that would impact the performance?
I mean, this is, thank you very much, first of all, very interesting question and very smart. I mean, the concept is, usually these kind of experiments are not done because, first of all, it's a limited application and it's a very specific case. And for me, it was more to give, not to highlight that it's like a representative scenario that everybody should test this kind of scenario, but for me, it was to give evidence that the Intumescent coatings behave a very specific way, and the physical and the chemical process that happen in these coatings they have to happen with a specific series. And for example, if you say this, take the same gradient, but you just flip it, the behavior would completely change. And I'm not aware of any other tests with exposure on both sides, honestly.
All right. Thank you for your answer. As another question come in, there is one regarding to the Tga experiments.
Yeah.
So basically what our attendee wonders is there is a strong second reaction peak in the nitrogen environment as opposed to the plot with air. What's the reason, and will that change will the change of surrounding gas environment in a real fire have an effect on the coating performance?
All right. So first of all, yes, definitely right that in the case of Tga in nitrogen, the second peak is much bigger, but because this is something that is typically seen in Tga experiments, that in the case of an oxidizing atmosphere, you don't only get the oxidation of the coating, but also oxygen has an influence on how the different decomposition processes would happen. I don't have a chemical knowledge and a chemical understanding, detailed chemical understanding of the coating that I can give you explanation on how this process would change on the molecular level or the chemical point of view. But what I can tell you is that having a low oxygen environment, since we have a higher peak here, it looks like that in a low oxygen environment, it would be a more, favorable scenario for the coating, because you have a faster and swelling, and also you don't have oxidation at the surface. So this is also, there is a bit of research on that, on how the oxygen level would affect the swelling of intumescent coating, and usually oxygen is a worse scenario than not having or having a low oxygen level for intumescent coatings. So again, this is another aspect tested in H3s, that is an open environment with high oxygen-rich environment, and for example, testing in a furnace with a very low oxygen levels would be a different scenario. And again, we have to understand which is the worst scenario for our coating or for our product, and we should always try to target that as a design scenario and not just get the best case scenario or the favorable one for your coating.
All right, thank you for your answer. I hope that has been clear. And one final question, more general sorts, to close this Q&A session and close up our presentation today. One of our attendees states that your observations are made under a lower temperature limit, while fire usually occurs in higher temperatures. So he asks if, from your observations, is it possible to predict the consequences caused by the fire, by a real fire in a building?
So very good point. Thank you for the question. So what I wanted to highlight to you is the coating, the temperature of the surface. So the concept of this research, I mean, the attendee is definitely right in terms of in a fire, we can expect higher temperatures than, for example, what I tested up to 900 degrees, let's say. And we can expect 1,000, 1,100 degrees in a typical compartment fire. And the concept of this research, it was to apply also, applying the constant incident heat fluxes is something that is something scientifically right, but of course it's hard to apply to the real or like engineering world, because we never have like a constant incident flux in the case of a fire. We always have like interesting or different curves of fire in a building. So what the approach of the research was to try to have some very controllable, well-defined thermal boundary conditions in order to understand the behavior on the fundamental level. And then if you have an understanding on the fundamental level, then this aspect can be sort of expanded to other conditions. And H3s can definitely go higher than these temperatures, and we can reach up to 1,000 degrees. And what I wanted to do is just mainly based on the H3s, based on the Tga experiments that I'll show you. Where is it? That I'll show you here. With my constant incident fluxes, I mainly wanted to target different temperature ranges to have different swelling stages or different swelling reactions, and in a way to see how different temperature ranges would have changed the swelling reaction and the performance in general. I hope I answered the question.
Thank you for your answer, Andrea.
You're welcome. Thank you, Julian, again, and the whole SFPE UQ chapter for inviting me. And yeah, looking forward to see the next presentations.
Thank you for your amazing presentation in name of the SFPE and for devoting your time for sharing your knowledge and all this experience during your PhD and after its completion. In name of the SFPE Student Chapter at UQ, I would also like to thank our attendees for joining us today. And I would like to let you know this presentation is going to be, well, it was recorded and it's going to be uploaded to our YouTube channel. I'm gonna show you in a second. So, oh, sorry, just, yeah. We are on YouTube as the SFPE Student Chapter. So you can look our previous talks from December 2019 and the two previous talks to this one. Soon we're going to have the recording of this session. Also, we are going to send an invitation for our next talk that is going to be the Friday, the 16th of April. And since you joined our event today, we are going to make sure you get the invitation for next one, where Dr. Mateo Gutierrez, another alumni from this institution, will present his experience during his PhD and his life in the CLT industry. So we're looking forward for you to join us in our next event as well.
Thank you.
Thank you very much.
Bye-bye.
Thank you, everyone. If anyone has any extra question, feel free to contact Andrea. For the sake of time, we are gonna end up this session right now. Thank you very much for joining us, and we are looking forward to see you in the future. Thank you.